All right, guys, welcome to your test review. You got a test review test tomorrow. So here is your review. I'm going to go through this pretty quickly. You can always rewatch it later. So what is an atom? Atom is the basic building block of all matter. We know that, right? So some characteristics. Everything in the universe is made of atom. An atom is made up of mostly empty space, right? Groups of atoms held together are called molecules, and elements are made up of only one type of atom. This is all review. So how has it changed? We started with Dalton, right? And his idea was that atoms were the smallest particles of matter. He saw them as fully solid spheres, right? And he did not know about the subatomic particles. He didn't think it could be broken down anymore. All right, but Thomson figured out that there were subatomic particles, right? He discovered electrons, but he thought they were in this like soup, right? So that was Thomson's theory. And then next we've got Rutherford. He did the gold foil, right? So don't forget that. Rutherford did the gold foil, and that's how he figured out that it's got that positively charged nucleus, and he theorized that the electrons orbited like planets around the sun. All right, next we've got Bohr, which we use his model a lot, and he said that the electrons moved within fixed orbits around the nucleus. Again, not exactly accurate, but it's closest to what we use now, right? Okay, so the modern theory states that electrons do not orbit the nucleus, but they move at high speeds to form an electron cloud. So they're actually in clouds of probability. All right, so what are the parts? We've got to know this, okay? The subatomic particles. So the three parts are the protons, the neutrons, and the electrons, right? These are positive. They've got a mass of 1 AMU. These have a 0 charge, right? And 1 AMU mass. And then these are negative, and they're 11836 AMU. So very, very light on the electrons, right? Center of the atom is called the nucleus, and inside the nucleus we've got the protons and the neutrons, right? Both of them are inside there. Okay. And the mass of an atom, of course, comes from the nucleus, the protons and the neutrons. All right, so here's the parts again, right? The plus signs are the protons, right? And these blue ones with no charge, these are the neutrons. And then we've got the electrons orbiting around. And this is where the mass comes from, right? So there we go, proton, neutron, electron. Okay. All right, so the proton symbol is P or P plus. I like this one because it tells us the charge, which is positive, and then the location is inside the nucleus, and the mass is 1 AMU. This is all review. Neutron, N or NO, I like this because of the charge. It doesn't have one, and again, in the nucleus, and the mass is the same, 1 AMU. The electron, E or E negative, I like this because they've got the negative charge. Location is outside of the nucleus, right, in that electron cloud, and the mass is very, very, very minimal. They might say 1/2000th, okay, AMU. It's very small. All right, so matter is made up of atoms. Yep, atoms are made of completely solid space. Not true. Electrons are larger. That's false. Nucleus of an atom is always positively charged. That's true. Most of the mass of an atom comes from the protons and the electrons. This is the part that's wrong, right? Most of the mass comes from the protons and neutrons. Neutrons have 0 charge. That's true. The model has not changed. That's false. Okay. So the Bohr model depicts all the components, right, of the atom. So that's different from the Lewis dot, okay? So it's got the protons, the neutrons, and the electrons in our Bohr model. All right, so we got to know how to read our element tile. There's the name, right? What's this? Atomic number, right? And that represents our positive charges, our protons, right? Down here, this is our mass. This is the protons plus neutrons. You've got to know that. Okay, so let's practice drawing our Bohr models, okay? First, we're going to look at sodium. We determine how many orbitals it's going to get by looking at the period. So let's see what period it's in. And we are in the 3rd period. Okay, so sodium's right here. Oops, sorry about that. In the 3rd period, right? All right, so let's figure out our components. For our protons, how do we figure that out? Right here, right? The atomic number, 11. Neutrons, how do we figure that out? We're going to take this and subtract that, right? So round that to 23 minus 11. That's going to give us 12. So we've got 12 neutrons. And then for our electrons, it's going to be the same as the protons. Okay, so that's how we come up with that. Next, we're going to draw our nucleus. Inside the nucleus, we put the protons and the neutrons. That's easy. And we already discovered we need 3 orbitals. So 1, 2, 3. Got to remember this. First energy level can only hold 2, right? First energy level can only hold 2. We got to get to 11. So let's put 8 in the next. 3, 4, 5, 6, 7, 8. So we've got a total of 8, 9, 10. So we just need one more in this outer orbital, and we're done with our sodium Bohr model. All right, next we've got carbon. Okay, let's see how many subatomic particles we've got. For protons, we look here, that's 6. For neutrons, we're going to take our mass, subtract, right? 12 minus 6 is 6. And then for our electrons, that's going to be equal to the protons. That's also going to be 6. So inside here, we've got our protons and our neutrons. And let's see, where is carbon? Carbon is here, right, in period 2. So we know that we're going to get 2 orbitals. Okay, we've got 6 electrons. Again, the first energy level can only hold 2. That leaves 4 for this outer orbital. And we're done. Okay, so know your properties. Okay, guys, these are the most reactive metals, right? These are the alkali. These are alkali earth. Pretty reactive, but not as reactive as alkali. Know that. These are your transitions, right? These are your transitions. Over here, we've got your halogens. Very reactive nonmetals, the most reactive nonmetals. And then over here, your noble gases, which are inert. Know that word. It means that they don't react. Okay? Noble gases don't react. All right, so know your groups and families. Okay? Know that each group is going to have similar characteristics. So as you go down a group, similar characteristic. As you go across a period, nothing is similar. Remember, we begin with very highly reactive metals, and we end a period with a completely unreactive gas. They have nothing in common, right? So we know that each group has the same number of valence electrons, and that is what makes them so similar. So all these groups, right? Groups or families, all very similar as you go down a group. Know where the metals are, the nonmetals, the metalloids, right? These are the metalloids. So know that. These in green, okay? And we already went over the alkali right here, alkali earth, transitions here. We've got the nonmetals all over here, right? We've got noble gases, halogens. Okay, know all that. Know the names of the families. Again, alkali, alkali earth, transitions, halogens, noble gases. Let's talk about the trends. We know the number of valence electrons is determined by the group number. Don't get thrown off by these guys. They're just Roman numerals. It means the same thing as this, okay? 1, 2. We skip the transition when we're talking about valence, right? 3, 4, 5, 6, 7, 8. That's how many valence electrons there are with this one exception, right? With this one exception, helium, of course, has 2 valence electrons. And remember, the valence electrons are only those outermost energy levels, okay? So you've got the nucleus, and then you've got 1, 2, 3 valence electrons. We're talking only about this outermost ring. The octet rule, know that. It means they're happy when they've got 8, right? That's why the noble gases don't react. Okay, so let's review drawing electron dot diagrams really quick. Okay, what we got here? Let's do a few of these. Helium. We'll do helium because helium is an exception, right? Because it's in group 8, But does it have 8 valence electrons? No, because it only has 2 protons, right? So it's only going to have 2 electrons. So 1, 2, because we're only doing valence for the Lewis dot structures, right? Let's do another one. Let's do argon right here, okay? Argon is in group 8, and it also has 8. So we put the symbol, and we fill in the dots, right? 4, 5, 5, 6, 7, 8, okay? And let's do one more. Let's do oxygen. Okay, oxygen. Oxygen is over here in group 6. So that tells us that oxygen has 6 valence electrons. 2, 3, 4, 5, 6. Remember, each side gets one before you give them a buddy. Okay, atomic radius. Know these trends, okay? The atomic radius increases as you go down in group, and it also increases as you go backwards across the periodic table. This is a little bit counterintuitive, so remember, down and to the left, okay, that's the atomic radius trend. Across a period, again, it decreases as you go to the right. It's kind of weird, but remember it, okay? All right, electronegativity. What is electronegativity? Electronegativity is the measure of a tendency for the atom to attract electrons to itself, okay? And they form negatively charged ions. A lot of times we're going to see oxygen like this, and that's because it's got 6 valence electrons. Remember when we did our Lewis dot structure? 1, 2, 3, 4, 5, 6. So guess what? It really wants one here and one here. So it has a strong electronegativity. So electronegativity, as you go this way on the periodic table, is going to increase. Okay? So if on your test it can give you just a little portion of the periodic table, okay? Whatever element is closest to this corner, that's going to be the most electronegative element, okay, which happens to be fluorine. But you'll have a periodic table. You don't have to memorize that. Just know that the trend for electronegativity is going up and to the right, right? Because this group here, think about it, really, really wants electrons, right? This group here really wants electrons, right? Because their orbitals are almost full. And again, the atomic radius, it's just the opposite. It goes backwards, okay, down and to the left. So here is a trend table for you. So you can, any trend that you want to study, it's right here, okay? So ionization energy and electronegativity, they go the same way, okay? Ionization energy is the energy that it takes to remove an electron. Again, since these guys in these groups are trying to gain electrons, they're going to have a high electronegativity, right, over here, because it's going to take a lot of energy to steal electrons from them. That's all that means, that word ionization energy. So just know that the trend is the same as the electronegativity. And then we know non-metallic character, of course, increases because we've got the non-metals over here. We know metallic character increases as you go down because we've got the metals over there. Remember, that staircase is the dividing line, right? So as you get away from that either way, you see those trends. Okay, remember the radius, and then the electron affinity is really just very similar to the electronegativity. All right, so I hope that helps. You guys can do this as many times as you want, but you have to complete it in class in order to get the grade for today. So be good for the sub, and if you're in first through fourth period. And you guys in the afternoon, I should see you, but I will be there for the test tomorrow, Lord willing. So I plan to be there. Okay, guys? All right. See you then.